Let's begin this story with Newton's law of gravity. According to Newton's law of gravity, all objects exert a force that attracts each other objects. This applies even to his well-known apple. This universal law of gravitation worked pretty well for predicting the motion of planets as well as objects on Earth. And it is still in use, for example making the calculations for a rocket launch. However, this theory didn't work for describing some scenarios in extreme regime of gravity. For an example, when it comes to describe the shift of Mercury's orbit. The actual shifting was faster than he predicted using Newton's law. However, in 1916 Einstein explained this phenomena with his different approach with space and time. Time as the fourth dimension in his relativity theory. Instead of using attraction force, he elaborated curving of the fabric of space and time as the reason. Thus, according to the theory of Einstein, it's kind of any kind of energy fall or bend into. Now, just think of big ball on a fabric and a small one is also projected. Big one creates a depression that draws the small one closer. Now we know what Einstein's perspective towards gravity. 100 years after the observation on the shift of Mercury's orbit which is elaborated previously, Einstein's theory of gravity just passed a black hole test with flying colors. Now, let's dig into this star and massive black hole new observation which has led to prove that the Einstein's theory is right again. By the observations using with European Southern Observatories or VSO, Very Large Telescope or VLT have revealed for the first time that a star orbiting the supermassive black hole at the center of our Milky Way moves just as predicted by Einstein's general theory of relativity. Its orbit is shaped like a rosette and not like an ellipse as predicted by Newton's theory of gravity. This is the animated orbit of that star called S2 around Sagittarius A, which lies about 26,000 light-years from Earth. Sagittarius A is a supermassive black hole of 4 million times the mass of the Sun. S2's orbit such that the location of its closest point to the supermassive black hole changes with each turn, such that the next orbit is rotated with regard to the previous one, creating a rosette shape. The data is gathered for 27 years by the astronomers using more than 330 measurements of S2's position and velocity with the aid of multiple VLT instruments. This is almost close to 3 decades of time. Those measurements was taken combining the light of all 4 8-meter VLT telescopes into a super telescope. This is equivalent to a resolution of a telescope with 130 meters in diameter. This new study, which was published in the journal Astronomy and Astrophysics. The research was conducted by an international team led by Frank Eisenhower with collaborators from France, Portugal, Germany and ESO. One of those VLTs is called gravity. That is why the research team was given its name as the Gravity Collaboration. These researchers keep high hopes that coming megascopes such as extremely large telescopes (ELTs) could allow astronomers to track stars that get even closer to Sagittarius A. If it works, we might capture stars close enough that can observe the rotation, the spin, of the black hole and define space and time around it. This would lead to a completely different level of testing Einstein's relativity. However, scientists know that at some point in a black hole, Einstein's general relativity might fail. This is the nature of science which we should admit. For the level of understanding now we have, the future is Einstein's theory. Earlier it was Newton's. We should admire and be grateful for all philosophers for their enormous service to the science. New philosophical ideas build on top of the base laid by others. Science is nothing without collaboration. Please consider subscribing to Science Hub channel for more educational and informative videos like this. Comment your ideas about this channel, where we should improve and your valuable ideas regarding the topic. Thank you for watching.